In this video, we will talk about deriving the acceleration constraint for a pulley with an incline. This is a little bit overkill as it was when we did the pulley without an incline, but it will show you some more about the techniques you might need for more complex problems. So firstly, I've already written out the free body diagrams for you, and I've written out the tension constraint. For this class, we probably will always have this constraint, and so we'll only need to figure out what the acceleration constraint is, and it's totally legitimate to just jump to just t, but I've written it out anyway. Let's go ahead and find the acceleration constraint. So as we discussed, to do that, we need to create coordinate systems. The difficulty, though, is if I create a coordinate system like I did before, like this, well, I have a slanted mass, and so it's going to be a bit difficult to find its position functions relative to that global coordinate system. Likewise, if I create a global coordinate system like this, it'll be difficult to find the position of this mass with respect to that coordinate system. It can be done, but it's more difficult. So here is an example where it will be useful to have local coordinate systems. So we're going to create two. First, for M2, we will create a coordinate system centered at the pulley that's going to look like this. So up is positive, to the right is positive. Whereas for my M1, we're also going to have a coordinate system with its origin centered at the pulley, but it's going to be a rotated coordinate system. I'm going to make it like this. Why? Well, it makes the to the right and over the pulley motion the positive direction, whereas for the blue, you can kind of see how to the rightward motion is still positive. So that's the main idea. I want my local coordinate systems to be such that they look like they're rotated versions of each other as you're going over the pulley. This makes the positive directions similar to each other and will thereby make the problem a little easier to solve. But it doesn't matter. You make coordinate systems according to convenience, and you'll still get the same results. So what's the position function of my M1 according to its local coordinate system? Well, its position function looks like this, x of t. And then what's my position function for my M2? Well, its position function looks like this, y of t. If then I look at the total length of my rope, which I know is constant, I will have L is equal to minus x1, for similar reasons as before, because x is negative in this coordinate system. Remember, it's measured with respect to that coordinate system, but minus x1 will be the length of the rope then from M1 up to the center of the pulley. And then for this part of the rope, notice I'm measuring it in the blue coordinate system. In the blue coordinate system, downward is negative. And if downward is negative, then this y coordinate here is going to be negative, and so I get minus y2 of t. And then finally, I have the constant part of my rope, which I can call c, and all together, that makes up the total length of my rope. I can then take a time derivative of both sides of my equation, and I'll get 0 is equal to minus v1 of t minus v2 of t. And then the derivative of c is constant, so it goes to 0. Then I take the derivative of both sides again, time derivative. And now I have a relationship between my a1 and a2. Adding a1 to the left, doesn't matter which one, I get a1 is equal to minus a2. And therefore they have the same magnitude but opposite directions. I can write my constraint as a1 is a and a2 is minus a. And so if I'm writing out my equations of motion then, for my red coordinate system, the x direction is going up the hill. And so I have t1 minus m1g sine theta is equal to m1a1. And then for my blue coordinate system, I'm looking at mass m2. I'm writing out its equations in the y direction. And so I have up as positive, down as negative, and then I get m2a2. And then I can plug in my constraints, and I get t minus m1g sine theta is equal to m1a, and I get t minus m2g is equal to m2 minus a, and I can divide by minus 1 on both sides to get the expected m2g minus t equals m2a. Now, just to emphasize that it doesn't matter where you place your coordinate system, what would happen if instead of having my red coordinate system with the origin on the pulley, what if I put the origin where my mass originally started moving? And what if For my blue coordinate system, instead of making the up direction positive, I had made the down direction positive, but I kept the origin on the center of the pulley. Well then, over here in the red coordinate system, the x position of the mast is no longer the length of the rope, or directly related to the length of the rope. Rather, wherever the position of your mast starts to wherever the center of the pulley is, let's call that a distance of d, you're going to need to take d and subtract the x position of your mast. So for example, your mast at some time is going to have an x position that's here on your ramp, right? Well, if it has an x position there on your ramp, then this blue line that I drew is your rope. So if you do the green minus the red, you'll get the blue line, which is the length of the rope that you're looking for. Is there anything else to worry about? No, there isn't, because I made my origin right here. So my x position is always going to be positive because it's to the right, and my mass will always be to the right of that origin. So it really is just d minus my x coordinate. So the length then becomes d minus x1 of t. All right, how about the y direction? Well, the y direction, now it's positive going down, and the length of my rope will just be my y coordinate. So I get plus y2. All right, so how does this change things? Well, d is a constant, so that's going to go away. The only thing that changes then is I get a plus sign for all of these, and then I get a1 is equal to a2. However, when I go to write Newton's second law for my equation for m2, and this new coordinate system down is now the positive direction. So over here, I now have plus m2g minus t2. So then when I go to plug in my constraint, I have a1 is equal to a2 is equal to a, because a1 is now equal to a2. So I get m2a over here, but this is positive and this is negative, which means I get m2g minus t equals m2a, which is the exact same thing that I had before. And likewise over here, nothing else really changed with this equation. So I still get the exact same thing as before. If you have the same systems of equations, you have the same solutions. You have changed nothing by changing the coordinate system.